Okay, so here are a few more integration by parts examples. So let's start with this one that says the antiderivative of x to the sixth times ln x dx. So good thing to try this and then come back, but basically what I know is that if u is ln x, du is 1 over x, and that's pretty good. So I'm going to let u be ln x. I'm going to let dv be x to the sixth dx. Now this means that du would be 1 over x dx, and that v would be x to the seventh over 7. So using that, I'm going to see if I can rewrite this. This should be the antiderivative. Nope. Should be uv, which is just x to the seventh over 7 ln x, minus the antiderivative of v du, which is x to the seventh over 7 times 1 over x dx. And that's just x to the seventh over 7 ln x minus 1/7 antiderivative of x to the sixth dx, which is nice and easy. So that's x to the seventh over 7 ln x minus 1/7 x to the seventh over 7 plus c, which is now x to the seventh over 7 ln x minus x to the seventh over 49 plus c. So basically, that just allows me to simplify my integral down quite a bit and leave some other pieces outside. Let's try one here. Let's try this example. Let's try the antiderivative of x squared times sine of 4x dx. Now, I don't think that I want u to be this, because then I'll have a cosine x, whereas if u is x squared, I might have better luck. So let's let u be x squared and dv be sine of 4x dx. Then du would be 2x dx, and v would be negative cosine of 4x divided by 4. So this would become uv, which is negative x squared cosine of 4x divided by 4, that's u times v, minus the antiderivative of v du. So that would be negative cosine of 4x divided by 4 times 2x dx. Now simplifying that, I get negative x squared cosine of 4x divided by 4 plus 1/2 antiderivative of cosine of 4x times x dx. 1/2 because it was 2 over 4. So that doesn't still look great, but it's a little bit better than this because this was an x squared and this is an x. So what if I repeat the process? I probably shouldn't use u and dv again, but I'm afraid I'm going to get confused if I don't. So I'm going to let u be x in this case, and dv be, I could put a little 1 here, dv sub 1 be cosine of 4x dx. Then du sub 1 is equal to dx, and v sub 1 is equal to sine of 4x divided by 4. And see, now v du is going to be something that I know how to integrate, and that's good. But I need to go to another page, so I'm going to do that. So what I had before was negative x squared cosine of 4x divided by 2 plus 1/2 times an integral that can now be written as, right, uv, u sub 1 v sub 1, which is x sine of 4x divided by 4, minus the antiderivative of v du, which was sine of 4x over 4 dx. But that's all multiplied by 1/2 because that was this, and this integration by parts again is just that integral. Now I have something that I can finally integrate, so I should get negative x squared cosine of 4x divided by 2 plus 1/8 sine of 4x times x minus the antiderivative of this, which is a positive now cosine of 4x divided by 16 plus c. So I think that is finally my antiderivative. Good night. What a nightmare problem. right. Well, should we try a couple more? I think so. How about the antiderivative of cosine squared theta d theta? Well, cosine squared theta d theta, I don't know, that's interesting. That could be cosine times cosine, so that might be a good one to think about. Or it could be cosine squared times d theta. But I think I'm going to try and let u be cosine theta and let dv be cosine theta as well. So then du would be negative sine theta, and v would be negative sine theta. Negative sine theta, yeah. No, positive sine theta. Well, I don't know if this is going to work, but I can try it. So this should be equal to uv, which is cosine theta sine theta, minus the antiderivative of v du, which is going to be plus sine squared theta d theta. So cosine squared theta, this antiderivative, is equal to cosine plus sine squared. Well, that didn't really help me because I ended up with sine squared. But maybe I can try again and see what happens. So what if I let u sub 1 be sine theta and dv sub 1 equals sine theta? Then du sub 1 would be cosine theta, and v sub 1 would be negative cosine theta, because I'm finding an antiderivative there. So this integral, so now what I have basically is the antiderivative of cosine squared theta d theta is equal to cosine theta sine theta plus this integral, but this integral is equal to uv, which was sine theta times negative cosine theta, minus the integral of v du, which should be then plus cosine squared theta d theta. Okay, here's the problem. I now have this on either side and this on either side, so I basically get 0 equals 0, and I haven't gotten anywhere. Bummer! It's really not helpful. So, sine squared, what do I think? Good night. How about we try Pythagorean identity? So we've got cosine squared theta is equal to cosine theta sine theta plus the antiderivative of cosine squared theta, sine squared theta. But remember, sine squared theta is actually cosine squared theta minus 1. Sine, is that right? No. 1 minus cosine squared theta d theta. Oh boy, I think I'm cooking with gas now. So I've got the antiderivative of cosine theta d theta is equal to cosine theta sine theta plus the antiderivative of d theta, because that's the 1 d theta, minus the antiderivative of cosine squared d theta, right, if I break that up. And now what I notice is what I want to solve for is on both sides of the equation. So check this out. Basically, what I can now say is that 2 times the integral of cosine squared theta d theta, if I add this over here, is equal to cosine theta sine theta plus the antiderivative of d theta, which is just theta, plus c. And now divide by 2, antiderivative of cosine squared theta d theta is simply equal to cosine theta sine theta plus c divided by 2. Oh my goodness. So sometimes you can kind of get the same thing on both sides and add it over and then divide by 2. But that is a pretty tricky situation. There's another way to do this too. You could use an identity to change cosine squared into like a cosine of 2 theta. But this is how to do it with integration by parts. All right, I think I've got one more in me. Let's try this antiderivative of e to the 2x times sine of 3x dx. Oh dear. Well, what do I want? What do I want? I don't know, so I'm just going to try u equals e to the 2x. And so du would be 2e to the 2x. If I let dv be sine of 3x dx, then I can have v be negative cosine of 3x divided by 3. Well, then this becomes uv minus the antiderivative of v du. Well, this is not super helpful, but I can simplify a little bit. Negative e to the 2x cosine of 3x over 3 plus the antiderivative of cosine of 3x over 3 times 2e to the 2x dx. I'm going to pull out a 2/3, so this is negative e to the 2x cosine of 3x divided by 3 plus 2/3 times the antiderivative of cosine of 3x e to the 2x dx. Now, this is still a pain, but what if I repeat the process? Right? Can I get something that will work? So what if I let u sub 1 be e to the 2x and dv sub 1 be cosine of 3x dx? Then du sub 1 would be 2e to the 2x. v sub 1 would be sine of 3x divided by 3. And this would become negative e to the 2x cosine of 3x over 3 plus 2/3 times this, which is uv minus the antiderivative of v du. v du, which is going to be 2/3 times sine of 3x e to the 2x dx. Now, this is the thing that's really tricky is this, remember, is equal to this. So this is equal to this. And this is what we're trying to solve for. And now it's on both sides of the equation. So if we were to write that whole equation out, what we would have is antiderivative e to the 2x sine of 3x dx is equal to negative e to the 2x cosine of 3x divided by 3 plus 2/3 e to the 2x sine of 3x all over 3 minus 4/9 integral sine of 3x e to the 2x dx. If I add this to this side, this is 9/9 plus 4/9 is 13/9 times the integral of e to the 2x sine of 3x dx. And that's equal to blob. So therefore, this integral, oh my goodness, is equal to 9/13 blob, where that is the blob, and that is a nasty problem. That's a hard problem. So those are some simple and complicated integration by parts problems, and now you can practice that in class.